On the forest floor, a lone ant moves in erratic, twitching circles. It stumbles over debris, appearing entirely disconnected from its own limbs. A hostile takeover is underway within the ant's central nervous system. Its biological circuitry has been intercepted and overridden. The source of the interference is a microscopic spore of the parasitic Ophiocordyceps fungus. At this stage, the ant's autonomy is gone. It is a passenger trapped in a body that no longer responds to its own will. To understand this behavior, we have to look at the fungus's core objective, spreading its spores to as many new hosts as possible. Reproduction is restricted by geography. Down at the soil level, the air is still, meaning any spores released here would simply fall back into the dirt rather than drifting to new victims. This logic tree illustrates how the fungus solves that problem. Lacking a brain, it relies on a biological algorithm to guide its next move. The first requirement, a mobile host, to carry it out of the stagnant air. By utilizing a host, the parasite transitions from a passive spore into an active tactician, systematically overcoming the physical constraints of its environment. The first active command of the takeover forces the ant to walk away from its colony, abandoning the safety of the nest forever. This isolation is a tactical necessity. If an infected ant stayed near the nest, the healthy workers would detect the threat and kill the host to prevent an outbreak. Once isolated, the fungus triggers the elevation phase. It steers the ant toward a plant stem and commands it to climb. This graph shows the environmental stakes of that climb. The fungus is searching for a specific Goldilocks zone, usually 25 centimeters above the ground. This height provides enough wind for dispersal without the extreme temperature fluctuations found higher up in the canopy. The fungus is now piloting the ant like a biological drone, navigating it toward a precise microclimate that will support the next stage of growth. The ant eventually reaches a leaf that sits exactly within that optimal environmental window. Here, the fungus initiates the death grip. It forces the ant's mandibles to clamp down with immense pressure onto the leaf's central vein. To prevent the ant from letting go, the fungus releases enzymes that dissolve the muscle tissue in the jaw. This transforms the bite into a permanent mechanical lock. This structural anchor is designed to endure. It must keep the body suspended through rain and wind as the ant's physical form begins to fail. With the host securely anchored, the fungus no longer needs it alive. It begins to systematically consume the ant's internal organs for fuel. The ant's final action isn't an act of survival, but a forced labor to provide the structural foundation for its killer's final weapon. The ant remains suspended like a trophy, a hollowed-out shell fixed to the underside of the leaf. From the base of the ant's head, the fruiting body erupts. A slender stalk pushes outward, fueled by nutrients harvested from the host's body. Over several weeks, the stalk matures and fills with thousands of infectious spores. Because of the ant's climb, these spores are now perfectly positioned above the forest floor. This trajectory map shows the payoff. As the stalk bursts, the spores fall in a targeted rain, directly onto the high-traffic foraging trails of the colony below. This process creates a self-sustaining loop. It is a system of natural mind control that uses an algorithmic approach to ensure the survival of the next generation. Below the leaf, the next set of victims marches through the invisible fallout, entirely unaware that the cycle has already begun again. How would you even begin to fight back against a parasite that can pilot your own body? Let me know your survival plan in the comments. If you want more deep dives into the darker side of biology, hit the subscribe button.